One question that's been looming is what are all the automorphic functions? As in, can we classify them? Can we list all of them? And here, when I'm thinking about automorphic functions, I'm thinking weight 0, level n, and character chi. Chi is even mod n. And so far, we've talked about Eisenstein series attached to cusps. So here, this frac A, this is a cusp of gamma naught n. And we've also talked about Moss forms. There's one easy one that we haven't mentioned yet, but is certainly present. If chi is trivial, then the constant function, say the constant function 1, the constant function 1, depending on how you define things, this is an automorphic form. And we can ask, is this everything? So the Eisenstein series, the Moss forms, and the constant function. And the very surprising answer, due to Selberg, is yes, in some sense. So we'll make this precise, and this will lead to this formula called spectral decomposition that's going to be really useful for doing calculations and getting access to things that we want to get access to. So let me start by talking about making this more precise, because this is imprecise. So this space of square integrable functions on the upper half plane mod gamma naught n that transforms with character chi has a subspace of what are called cusp forms. And this subspace of cusp forms is going to be the functions in the space which satisfy that the integral along any horizontal line or line segment from 0 to 1 of f of x plus iy dx for any positive y is 0. So basically, this is saying that they have no constant term. Because recall that when we were talking about eigenfunctions of the Laplacian, we said that all of these automorphic forms are going to have some spectral expansion, and there's an e to the 2 pi I n x term, you're summing over n, and then the n equals 0 term, you have a y to the s and a y to the 1 minus s. So this is saying that that part, the y to the s and the y to the 1 minus s, those don't appear in the Fourier expansion. So this is the cuspal subspace of this. And so here's a theorem, which is that Moss forms span the cuspidal subspace. And this is not at all obvious, and it's quite difficult. And then so this is sort of part one of Selberg's spectral decomposition, or this is maybe the setup for Selberg's spectral decomposition. So Selberg's spectral decomposition says, suppose that you have some function v that is square integrable on this space with character chi, and you're going to choose some complete orthogonal basis of Moss forms. For the cuspidal subspace. So when I write this, why does this make sense? Well, we said that our space here has an inner product, the Peterson inner product, and that this space is a complete C vector space with that inner product. So it's a Hilbert space. So saying that the Moss forms span the cuspidal subspace, we can choose a basis, and it's complete in the sense that our inner product is complete, and it's orthogonal with respect to that Peterson inner product. And it makes sense to write this as just the set like this. I mean, here we can think of J going from 1 to infinity because the eigenvalues of the Moss forms are discrete. So we can just enumerate them, say enumerate them in ascending order, and it'll make sense to think of J being an integer here. So we're supposing that V is a square integrable function that's automorphic with character chi, and we have chosen some complete orthogonal basis of Moss forms. Then this is the punchline of Selberg spectral decomposition. The function v, evaluated at a point z, we can write as a sum over this basis. And again, it makes sense to write it as a sum because the Moss forms are discrete. And then here we have this inner product. Some authors will ask that the basis is orthonormal, and then this term doesn't appear. It's largely taste. I find it a little bit easier to write it this way. It's a little bit more explicit. So we have this term coming from the Moss forms, and then we have a term coming from the Eisenstein series. So we have to sum over the cusps frac A of gamma naught n, and then we have an integral 1/2 minus I infinity to 1/2 plus I infinity. And here we take an inner product of V with the Eisenstein series at the cusp A, and then I'll put a little dot here to indicate that the inner product is being taken with respect to z, then the rest of this is like this, and then this is an integral in lambda. And then if chi is trivial, you also get a term coming from the constant function. So the constant. So this is you can write this as the inner product of v and 1 with the inner product of 1 and 1. This is just the volume of the space. And this only appears if chi is trivial. And you don't get this term otherwise. So this theorem is going to be really, really useful for us, because very often what will happen is that we will have these functions v that we're really interested in, but we don't know anything about. We can prove that they're automorphic, and we can prove that they're square integrable, and we won't know any of their properties beyond that, pretty much. This Selberg spectral decomposition is essentially choosing a basis in the same way that you would choose a basis for any vector space, and expressing the vector that you care about as a sum of these basis vectors. And by knowing stuff about the individual basis elements, you can reconstruct the knowledge that you need about the function that you actually care about. So this is great. This is going to be the main tool that we use to translate functions that have some arithmetic content encoded in them into analytic results that we can actually calculate and get an answer out of. And we're going to do that by sort of figuring out what each of these pieces are in the spectral decomposition, and then put them together appropriately to recover our function of interest.